Hi everybody, welcome to our next lecture. And in this lecture, I want to recap section 4.1 in our text, which introduces random variables, particularly discrete variables, and probability distributions. So the outcome of a probability experiment is often a count or a measure. When this occurs, the outcome is called a random variable. And just like in an algebra class, we tend to use x a lot here as well. So a random variable x represents a value associated with each outcome of an experiment. And the word random indicates that x is determined by chance. So for instance, let's say I flip a coin 10 times. X could represent the number of times that a tails comes up, right? So x could be 1 out of 10. It could be, x could be 6, meaning 6 out of 10, etc. There are two types of random variables, discrete and continuous. So a random variable is discrete when it has a finite or countable number of possible outcomes that can be listed. The idea here of listing things is actually really important. So for instance, if my possible x values, like in the example I did for flipping a coin, could be 0 tails, 1 tail, 2 tails, 3 tails, and so on, those values tend to be all whole numbers, and we can actually list them all out. The other thing you want to notice with discrete variables is that you do have gaps between possible x values, right? So in my flipping coin example, for instance, we could have 0 tails, 1 tail, 2 tails, 3 tails, and so on. There's gaps between there. We're counting by ones. We're not allowing for fractions or decimals. It doesn't make sense, right? How can you have half of a tails? It doesn't work. So there's typically gaps between your x values. When you're talking about continuous, this would be an uncountable number of possible outcomes. It's something that we could not list. It's not possible. And it's often represented by intervals on a number line rather than individual points. The other thing that happens here too is that basically you can break down your possible x values into smaller and smaller decimals. So we're allowing decimals here. We're allowing fractions here as well. And not just that, but smaller and smaller instances of them. And you want to think about this more as a theoretical idea. So I know in the real world, we're not going to use, 20 decimal places or something like that realistically, right? Or infinitely many decimal places. That's just not going to happen. But it's the idea of like theoretically, could we break this down smaller? In most applications, discrete data is counted, whereas continuous data tends to be measured, right? So let's measure your height, for instance, in general. So here are two examples. The first one would be the attendance at a rock group concert, or any concerts. So if you think about concerts, people attend concerts and we count people using whole numbers, right? We can't have half a person. That doesn't make sense. So something like this would be discrete data. In the second example, we have length of time. Student athletes practice each week. And in this case, length of time, for instance, we could talk about in hours, or you could talk about it in minutes, in seconds, in fractions of seconds, and so on. So you can really break time down into smaller and smaller units. And in that case, you have continuous data. Now, discrete data tends to be the focus of chapter 4, which was what we're going to focus on for the rest of the video. And continuous data tends to be the focus of chapter 5 here. So we'll look at that another time. So let's talk about some discrete probability distribution definitions and information. So like I already mentioned, we'll talk about continuous later. They do use totally pretty much very different strategies. Some of the stuff overlaps, but they are very different in how we do calculations and things. So we'll focus on discrete here and then continuous later. So each value of a discrete random variable can be assigned a probability. And by listing each value of the random variable with its corresponding probability, you form a discrete probability distribution. When we hear distribution in stats, you can sort of just think of it as a table. So basically, one column is going to be all your x values, and the other column is going to be your probabilities that are associated with that particular x value. Additionally, we have to satisfy the following conditions. So the probabilities of each random variable are always between 0 and 1. So that's nothing new there. We know probabilities are always between 0 and 1. So that's a good check to make sure you haven't done anything wrong. But the other big thing here is that the sum of your probabilities is 1. So all those probabilities in the table should add up to be 1. And these are the two things that really check that you do, in fact, have a correct probability distribution. The reason they add up to 1 is because we're looking at a whole there. The x should be all the possible x values for that particular experiment. So when you add up the probabilities, it should equal 1 so that we have a whole or all of them included. Now, our next two examples here are not probability distributions. They each have a mistake. So if you go through them and take your time with it, we're going to check these two different options here. So in the first case, if I look at my probabilities, and I'm just going to circle them. Now here we have a table that goes horizontally. So instead of it going vertically like this, it does go horizontally. So our x values are on top and our probabilities are on the bottom. Now, I have no issues with the probabilities themselves, right? They are definitely all between 0 and 1. But if I go to add these up, well, this is already 1 right here. 0.75 plus 0.25 is 1. So we're going to be way over 1. So that is why this example is not a probability distribution. So there's definitely some mistakes somewhere, or maybe this data should not be a probability distribution. So either you made mistakes or you're using the data in the wrong way. In the second example, most of our probabilities look fine, but this one here is problematic because it's negative, right? You cannot have a negative probability. It just doesn't make sense. So again, here's the problem with this distribution. Again, it just doesn't work. So this one is incorrect. Now in the next example, we'll actually create our own distribution and see how it works. So in this case, we're going to construct a probability distribution for the following data. You have the overtime hours that are worked by various employees. This would be our X here. And then the second one is your frequency count. So when you have a table like this that you're starting with, again, these are not probabilities, right? They're not in probability form. These are counts. So what we're saying here basically is that 6 employees had 0 hours of overtime. 12 employees had 1 hour of overtime. 29 employees had 2 hours of overtime, and so on. So here you just have a standard frequency distribution where one of the values is your X or your variable and the other is a count, it's your frequencies. Now you can keep your table going horizontally or vertically, it really doesn't matter. I tend to like vertical tables as a preference. So I'm going to go ahead and start there. And I'm going to rewrite all my X values. So I have 0, 1, 2, 3, 4, 5, and 6. And then for probabilities, remember a probability is always a part to total. So the first thing I have to do is figure out my total here because it doesn't give it to me. So your total would be your sum of the frequencies. So if I add up the 6, the 12, the 29, the 57, and so on, that would give me my total, which is 192. And then your part for each one is going to be the count number, so the frequency. So for 0, it would be 6 out of 192, which is about 0.031. For 1, it's 12, so it'd be 12 out of 192, which is about 0.63. And I just used my calculator here to get these answers, and I'm rounding to 3 decimal places. For 2, my count is 29, so 29 over 192, about 0.151. For 3, it's 57 for 192, so about 0.297. For 4, it's 42 over 192, just 0.219. For 5, it's 30 over 192, which is about 0.156. And then for the last one, we had 16 employees who had 6 hours of overtime, which is about 0.083. So this would be our final probability distribution here. So you have your X values and then you have your final probability answers. Now, as a side note here, how would this look if it went horizontally? Just so you can see it. So your x values are 0, 1, 2, 3, 4, 5, and 6. And our first probability is 0.031, and then 0.063, 0.151, 0.297, 0.219. I should have made my table bigger, 0.156, and 0.083. So you could also write that table horizontally. They're both correct, and you should be able to read both forms of the table, whether it's vertical or horizontal. Now, the last thing I want to talk about in this video is how you actually can find the mean and the standard deviation or variance from a probability distribution. So this basically kind of puts chapters 2 and 3 together in a way, right? Looking at some of those formulas we saw in chapter 2 and combining them with probabilities here. So the mean of a discrete random variable is given by this formula here. What you do, just to clarify, is you start by multiplying each x value by the probability. So you do that, and then you're going to add up all of those. So you multiply first, and then you add everything up. And then you'll see a similar relationship between variance and standard deviation as we have in the past. One of them is the squared version of the other. It starts very normally to how we're used to, where you subtract the mean first and square it. But here the changes is that you're then going to multiply by that probability as well. And again, that summing part is the last thing you're doing. You're going to subtract the mean and square it, then you're going to multiply by the probability, and then we'll add everything up at the end. So let's do that last piece with this example. Here we have games play, that would be your x, and then you can see that they are giving us the probability here. You can verify that this actually is a probability distribution. So all the probabilities are between 0 and 1, and if you add it up, you should get 1. So we're going to go ahead and proceed from here. So to find the mean, all we're going to do is we're basically going to multiply each of these pairs together. So you're going to take the x value and multiply it by its probability. So 4 times 0.18, then we're going to add it with 5 times 0.223, add it with 6 times 0.214, 7 times 0.38, and finally 8 times 0.027. And we're just going to use our calculator here, so I encourage you to try that at home. Make sure you're using the calculator correctly. And what you get there is 5.803. So the mean is a pretty quick calculation. The standard deviation and variance do take a little bit more work. So the first thing we're going to do is we're going to subtract each x value with the mean. Now again, you don't have to do this over and over. Just do it once for each x value. So I'm going to do the 4 first. So I do 4 minus, and your mean is something that you probably will have to calculate. And when I subtract, I get negative 803. I do the 5 minus 5.803. So I get negative 0.803. When I subtract with 6, I get 0.214. When I subtract with 7, I get, sorry, not 0.214 here, I apologize. Can't my raw numbers, 0.197. That looks better. Here would be 1.197. And then finally 8 minus 5.803. And again, I did this up before class. So you would just go ahead and use your calculator and do all that subtraction. And then your next step, don't forget, is to take that subtracted value and square it. So again, we're going to take that value. I recommend using as many decimal places as you can, because you can always round at the end. But if you use too few decimal places and the final answer wants you to use like 3 decimals or 4 in your final answer, you're not going to have enough. So use extra decimal places. You can always round at the end. So when I square this first value, I get 3.250809. For the second value, 0.644809. The third value, 0.03, 8809. Then 1.4320809. and finally 4.826809. And then here's where it changes. Now we're going to multiply by the probability. So for my value of 4, I'm multiplying by 0.188. For the 5, I'm multiplying by 0.223. For the 6, 0.214. For the 7, 0.348. And then for the 8, 0.027. Now I'm just going to multiply again right across here. And what I get is 0.61115 for the first one. Let's continue down. Oh, I forgot to write my answers up for the other ones. I guess I skipped that piece. Let me do it now with you guys. 0.644809 times 0.223. So for the second one, 0.143792. And I'm just going to stop after what I think I have 6 decimal places there. That should be more than enough. For the next one, I have 0.008305. For the next one, 0.498615. And for the last one, 0.13032, or around there. So those are the values that I'm getting. And then if you add up all these values, you should get about 1.39219. Again, depending on how many decimal places you use, you should be pretty close to this, which is about 1.4. So I'll just round to 1 decimal place here. Now, the value that you're doing here, this is your variance. So our variance, which is sigma squared, is about 1.4. Now, to get the standard deviation, what we're going to do is just take the square root of this. And again, here you may want to use a few more decimal places just to ensure it is more accurate. When we do that, we get about 1.18 here, which is about 1.2. So here is our variance. Here's our standard deviation. And up here we saw, I guess we can round this at this point to 5.8. We'll kind of be consistent there. Is our mean. So the variance does take a little bit of time. I don't have a shortcut formula for Excel. You can manually do it in Excel if you're pretty good with it and do your multiplication and things there. But I don't have an easier shortcut. So we'll just do these by hand. Now, the last little piece I just want to note is on expected value. So expected value is what you would expect to happen as an outcome over thousands of trials. It's also equal to the mean. So if you see expected value here, what they're really referring to is the mean, and it's the same exact formula as the mean. So when you see questions on that, don't get overwhelmed. Don't think, I haven't seen this before. You're basically just doing the calculation for the mean there to answer that question. So I hope this was helpful to just kind of recap what we covered in 4.1 and just probability distributions overall, as well as discrete variables here. But if you have questions, always remember that you can reach out.